Hi, I am Dr. Saroja, retired professor in chemistry. Let's see today what is entropy in second law of thermodynamics. Let's see what is conversion of heat into work. The identification of entropy was first attributed to Rudolf Clausius in 1822 to 1888, a German mathematician, and he is a physicist. He studied the conversion of heat into work. He recognized that heat always flows naturally from a higher temperature to lower temperature. But if you need to heat a cold object like cold coffee, you need to supply heat energy.
It's 3 o'clock.
He stated that heat does not pass from a body at a lower temperature to higher temperature without an accompanying change elsewhere without supply of energy. He observed that in a heat-powered device, only a percentage of energy gets converted into work and the remaining is left to the surroundings. Heat cannot be completely converted into work. A part of it goes a waste, and hence the efficiency of this conversion is always below 1. It is never 1. Let's see what is entropy. It's represented by a symbol capital S. Nicolas Leonard Sadi Carnot, 1796 to 1832. He is a French chemist. He is the father of thermodynamics. He is responsible for the origins of second law of thermodynamics. He first hit upon the idea of thermodynamic efficiency in a steam engine, or it's also called Carnot engine. It's a physical law based on universal experience concerning heat and energy interconversion. The randomness in a system is called entropy. It is represented by a symbol capital S. It affects all aspects of our daily lives, which we will discuss in the coming slides. Second law of thermodynamics states that entropy of the entire universe as an isolated system will always increase in a spontaneous process. Change in entropy is always positive. Delta S, change in entropy, is always positive. Let's see what is a spontaneous process. A spontaneous process takes place by itself automatically. Like an ice cube left at room temperature melts automatically. We get older with age and we get never younger. Water will spontaneously splash and flow down a waterfall, but it will never go up the fall, never collects itself and go up the cliff. A bouncing ball will come to rest, but a ball at rest will not suddenly start bouncing. Heat will always flow spontaneously from a hotter body to a colder body to the surroundings, but the thermal energy in the surroundings will not spontaneously concentrate itself and flow into a hot place, or heat will not flow from cold body to a hot body. None of these processes violate the first law, but they do violate the second law. The processes take place spontaneously only in one direction. What is randomness in a system? All naturally occurring processes are spontaneous, and all spontaneous processes are irreversible. They tend to occur in a direction that leads to maximum disorder or maximum chaos in the system. When water spills from a cup, it spreads out randomly over the floor. It doesn't stay as one mound in one place. It will not collect itself together and refill the cup. All over that is spread, it will not collect itself and come back into the cup. If a gas balloon leaks, or if a gas from scent bottle leaks, gas diffuses randomly throughout the room, but the reverse doesn't happen. The gas doesn't go back and fill the balloon. The scent doesn't go back into the scent bottle. Let's see what is change in entropy. Entropy is a state function. It depends only on the state of the system. The greater the disorder, the greater is the entropy of the system. The change in entropy during a reaction is represented by delta S. Delta always represents change. Delta S is equal to entropy of products minus entropy of reactants. During the reaction where the total number of product molecules is greater than the total number of reactant molecules, the disorder always increases, order decreases, and delta S is always positive. An exception to this rule is when a gas is produced from non-gas reactants, zinc solid plus 2HCl giving 2HCl liquid giving zinc chloride solid plus hydrogen gas. Here the change in the number of molecules, let's see. On the product side we have 2 molecules, on the reactant side we have 3 molecules. So product minus reactant is equal to change in number of molecules is equal to minus 1. So the number of molecules, though they are number of product molecules are actually here lesser and here they are more, but delta S is still positive. That's because hydrogen is a gas and gas has greater entropy. All others are non-gas reactants. Therefore, entropy increases, though the number of molecules of the product are lesser than the number of molecules of the reactant. This is an exception. Standard entropy is measured at 298 degrees Kelvin and 1 bar, that is 1 atmosphere almost of pressure, and it is given a symbol S0 with 0 as the superscript. Now let's see what are the processes that decrease the entropy. The freezing, where liquid becomes solid. Solid because the particles are in a very orderly, arranged in a very orderly manner. The randomness is less, therefore entropy is less. Whereas liquid, the particles are all scattered, therefore entropy is more. So in freezing, where the liquid becomes solid, entropy decreases. In condensation, where gas becomes liquid, here also entropy decreases. Gas has more entropy and liquid has less entropy. Crystallization, where the molecules from the liquid state, they attain an orderly state and form a crystal. Therefore, the entropy decreases. Addition reactions, where 2 molecules combine to form 1 molecule, entropy decreases. Reactions that reduce the number of gas molecules also, entropy decreases because the gas molecules have more entropy. Particles in solution have more entropy than undissolved solids. 2 moles of a substance has more entropy than 1 mole of it. Photosynthesis is where carbon and water in disordered state combine to form more ordered sugar molecules, therefore entropy decreases. So these are some of the reactions, processes where entropy decreases. Now let's see what happens to entropy in a reversible process. Let's take the combination of nitrogen and hydrogen to form ammonia. 1 molecule of nitrogen gas combines with 3 molecules of hydrogen gas, giving 2 molecules of ammonia gas. 4 molecules in all of the reactant are forming 2 molecules of the product, and the entropy is decreasing for the forward reaction and increases for the backward reaction. The value of entropy for the reverse reaction has the same magnitude, quantity is the same as that of the forward reaction, but the sign is opposite. Delta S for the reverse reaction is minus delta S of the forward reaction. Entropy always increases in nature. Reactions can occur with decrease in entropy also, but we have to supply energy. Or reactions that occur with gain in energy, if they make more stable bonds, also the entropy decreases because the bonds are very stable, so there is more order. Let's see how to calculate entropy. In an isothermal reversible process, change in entropy is equal to delta S is equal to entropy in the final state minus entropy in the initial state. It is the change in amount of heat divided by absolute temperature. For an infinitesimally small change, infinitesimally small is represented in calculus by differential. So differential of entropy is equal to infinitesimally small change in entropy is equal to differential of Q reversible, that is differential small amount of heat absorbed divided by absolute temperature. For a change to be measurable between initial and final states, we have to integrate this expression. The integrated expression is ds, if you integrate it becomes delta S, and integral of dq reversible by T, that becomes Q reversible by T. That is the amount of heat absorbed divided by absolute temperature at which it is absorbed. Let's calculate the latent heat of let's calculate the entropy change for ice becoming water. Latent heat of fusion of ice at 0 degrees centigrade is equal to 334 joules per gram for 1 water molecule, that is 1 solid water, that is ice becoming liquid water. H2O solid giving H2O liquid. Delta S is equal to 334 joules per gram is the heat absorbed divided by the temperature at which it is absorbed is 0 degrees centigrade, that is 273 Kelvin. So it is equal to 1.2 joules per Kelvin. This is the change in entropy for fusion of ice. Now entropy, let's come to our experience. Entropy is all around us. In all the processes that occur in nature, there is increase in entropy, increase in randomness. For example, cells within our body are dying and they're degrading all the time, and it's an irreversible process. The cells do not form themselves in the body. Environment is all the time degrading. The floor always gets dirty and coffee always gets cold. All these processes occur with increase in chaos. People make mistakes. Businesses are failing. Crime rate increases. It is increasing constantly. Revolutions are occurring. All these occur with increase in randomness or chaos. Relationships are ending. Entire universe is marching towards a collapse. All this is happening with increase in entropy. We cannot prevent entropy, but we can curb, we can control, we can work with the processes that are increasing entropy, and we can understand them and control them. For example, we can clear up the messy desk that is in a disorderly manner and bring some order into it. Similarly, if the coffee got cold by itself in a spontaneous process, we can reheat. By supplying some energy, we can reheat it. Similarly, we can rectify our mistakes. And environment also, by being extremely conscious about the environmental degradation, we can stop the degradation of the environment. And relationships also, we can work and better the relationships. We can clear up the entropy. Thank you so much for a patient hearing, and if you like my video, please subscribe. And in the next video, I'll come up with another important thermodynamic property, that is free energy. Until then, bye bye.